Hello, students. Today is Tuesday, May 11th. This is the class video for AP Chemistry. So reminder, tomorrow we will have superstar Mr. Scotty Nichols from Mass Insight to give us a exam review. I am giving you the incentive of 10 extra credit points or 2 extra dropped homework assignments. What a deal. Take advantage. It's going to be a fabulous review. He's going to go over exam strategies. He'll go over the format of the paper exam and the digital exam. And I'm sure we will learn a lot from him. All right, so in this class, we started by going over FRQ number 2 from the previous homework. The answer key is on the slides in Google Classroom, so feel free to look at the answer key to FRQ number 2 if you wanted to look at any questions in more detail. All right, and then we did this pair deck. So we have a voltaic cell here, and silver metal is reduced. Notice there's, okay, this is just measuring voltage. Okay, there's no power source here. Okay, this is a cell that is just driven by the spontaneity, the thermodynamic favorability of this reaction. So it's saying that silver metal is reduced in this voltaic cell. So we have Ag plus an electron, and we're getting silver metal, which is collecting on the surface of this silver electrode. And the question asks, label the anode, the cathode, and the salt bridge. So first of all, remember our nice mnemonic, an, ox, red, cat. Okay, so since Ag is getting reduced, this is the cathode, and our other electrode must be the anode. Okay, where oxidation is occurring of the tin, the SN electrode there. And then our salt bridge, right, that's this thing in the middle, right there, that connects to 2 half cells. All right, next part asks, given the half reactions and reduction potential, calculate E cell. So E cell, again, is going to be, and this is the standard cell potential, so I should have a little circle there. E cell is equal to the reduction potential minus the oxidation potential. Okay, so here we have the reduction potential, right? Our silver is getting reduced and our tin is getting oxidized, right? Right, we actually have to flip this reaction to show what's actually happening. So minus 0.14 volts, okay, and we get positive 0.94 volts, which we would expect as positive E cell because that indicates thermodynamic favorability. All right, what's the net ionic equation? So again, here's our reduction. This is our, okay, this is written as a reduction. So the actual oxidation that's occurring is, right, we have to flip this reaction. The actual oxidation that's occurring is that SN is turning into SN2 plus 2 electrons, right? There's our oxidation. Our reduction is this Ag plus an electron goes to Ag solid. Okay, and notice in order for us to write the balanced, right, we need charge balance, right? We need to balance the electrons, right? Because the number of electrons produced by the oxidation has to be transferred to the reduction. So we're going to take this second equation and multiply by 2. Okay, and then when we multiply by 2, right, this is going to become 2 Ag plus 2 electrons, and this is going to become 2 Ag solid, right? And this just stays the same. So then now we can add these together. our electrons cancel out. So our net ionic equation, I'll write it up here, is Sn solid plus 2Ag plus produces tin plus 2 and 2Ag. There's our net ionic equation right there. Moving and which way the ions in the salt bridge are moving. Okay, so recall from our net ionic equation, here are the two half reactions that are happening. Here's the oxidation, here's the reduction. The electrons always move from the anode to the cathode, okay, because at the anode we have oxidation occurring. We are producing the electrons here at the anode, and then they travel up, go through the wire, and then they reduce the silver ions over at the cathode. So always anode to the cathode. I'm sure you can make up some kind of rhyme or song about that. Okay, so the electrons are moving this way. Which way are the ions in the salt bridge moving? On this side, right, we are adding electrons in. This side, this cell is becoming more negative as we add electrons. Okay, in order to maintain charge neutrality, to balance out the charge, we need to add in, okay, we need to have positive ions migrate in here to make the charge neutral again, okay? And so positive ions, okay, cations will go this way, anions will go this way because on the anode side, on the oxidation side, right, we are losing those electrons, we're gaining positive ions. We need negative ions to come here and provide that charge neutrality to balance out the charge on the positive tin ions. Okay, so for the salt bridge, the negative ions, the anions, go towards the anode. Okay, the positive ions, okay, go towards the cathode side. All right, what causes the mass of the SN, the tin electrode, to decrease? Okay, as we mentioned, right, again here it goes back to the half reactions. On the right-hand side where the cathode is, where the reduction is taking place, the silver is gaining mass because silver ions are turning into solid silver at the surface of this electrode. Over here, the oxidation of the tin produces tin ions which go into solution, right? These solid tin atoms now become aqueous ions that just go into solution and dissolve in there. So now it turns out that we can take the free energy and relate it to K, the equilibrium constant. And so we can see this relationship between all three of these quantities, K, delta G, and E cell, and they're related by these different formulas. On your equation sheet, you have this one. Okay, you also have this one. You have the Nernst equation here, which is the cell potential at non-standard conditions, and we'll look at that in a bit. And also don't forget that delta G is equal to delta H minus T delta S. And so we can use our delta G equals minus RT natural log of K equation to figure out what K is. Just put this in here, and it's e to the minus delta G over RT. Okay, and R is 8.314 joules per mole Kelvin, and temperature is 25 degrees C, but we need to change that to Kelvin. So that's 298 Kelvin. And plugging in here, I'm not going to plug the numbers in, but I'll give you the answer for K. You will end up with 6 times 10 to the 31st. So a huge equilibrium constant, okay, indicating that this is a very product-favored reaction, which we would expect since delta G is negative and spontaneous. So this reaction is favored, okay, in the forward direction. And we can also see that from the positive cell potential. All right, so the next topic in Unit 9 is electrolysis. So electrolysis is another type of electrochemical cell. And the very first thing we're going to do is distinguish the two. So remember, with a voltaic cell, we were looking at a thermodynamically favorable reaction. An electrolytic cell is going to use electricity to drive, okay? There's going to be a voltage source that drives a thermodynamically unfavorable reaction. Okay, so we'll take a look at the electrolytic cell. All right, so electrolysis uses direct electrical current to drive a non-spontaneous redox reaction. So electricity is supplied. Here's a voltage source right here shown in this reaction, and it forces the electrons to go in the direction that they would not normally go. And it's a very important process in industry, especially for purifying elements, such as probably one of the most industrially important uses of electrolysis. One of the most is the purification of aluminum from bauxite. Bauxite is the aluminum ore, and so electrolysis is used to separate pure aluminum from the aluminum oxide ore that people mine in the earth. So how is this different from, this is an electrolytic cell. How is this cell different from a voltaic cell? First of all, it requires a voltage source, okay? It takes place in liquid or solution with no salt bridge, okay? There is no salt bridge here. And then finally, the cell voltage, okay? And I'm going to put a minimum here because it's not, the electrolytic cells are not necessarily used at standard conditions or operate at standard conditions. So it's kind of a misleading thing to call it the standard cell potential. But the minimum, we can make an estimate of the minimum voltage required to drive this. So the minimum voltage source that we need to supply. that is always going to be less than 0 because, right, we are driving a non-spontaneous, unfavorable reaction. Okay, but just like the voltaic cell, oxidation still occurs at the anode and reduction still occurs at the cathode. All right, so here in this electrolytic cell, the reductions, okay, these are the reductions from the table, the standard reduction potentials. We've got to take a look at what's happening in this cell to figure out, what reaction to flip here. Okay, so you can see that chloride ion is turning into chlorine gas. It is getting oxidized. Okay, so here's the oxidation happening. So this is the anode, as indicated over here. And so here on the right-hand side, there's the reduction of sodium cation to sodium molten liquid. So we've got this reaction is occurring right here. And we've got to flip this reaction over here. So let me write the flipped reaction. So 2Cl minus produces Cl2 gas plus 2 electrons. So you can see here that's going to be a minus 1.36 volts. And so when we get this E cell, okay, this is going to be the minimum voltage. That's going to be a minus, what's that going to be if I do my math correctly? 4.07 volts. Okay, so at minimum, to run this reaction producing chlorine gas and sodium liquid metal, you'd have to put in at least -4 volts. Now, we're doing this in order to purify some pure sodium. Also, we can obtain chlorine gas from this reaction, okay? In the opposite direction, we would only get the aqueous ions, okay? And that's not what we want, right? If we want to get sodium metal to make a battery or to use it for, it's a powerful reducing agent. So if we want that pure metal, right, we're going to have to drive those ions to forming those pure elements, right, through the use of electrolysis, through the use of electricity to drive those electrons in a direction that they would normally not want to go, right? In nature, chloride wants to stay chloride and sodium ion wants to stay sodium ion. It does not want to form these things naturally. So we've got to force it to go in the thermodynamically unfavorable direction to get it to happen. So that minimum voltage here is the E cell. Okay, so got to put in at least 4.07 volts to drive this reaction. And in reality, you're going to have to probably put in quite a bit more because, right, there are other things that we need to do, like there's some activation energy that we need to supply for this reaction to happen. So this is just a minimum voltage here. All right, so again here, we've got this reaction, and we are going to go over this calculation on Thursday. So I won't do it out here, but the main purpose of this calculation is to figure out, okay, if I want this amount of sodium metal, okay, then how long do I need to run this reaction, okay, to get this amount of sodium metal? And what current do I need to apply to get this to happen at a reasonable, time span? All right, so electrolysis is used for many things, and you can see here in the left, this is a way to nickel plate something. Okay, so we can put it in aqueous nickel sulfate. We have a nickel anode, and then we put the object that we want to plate on the cathode, and we get right? We force the electrons out of the nickel metal and onto the object that we want to plate, and we end up with a nice nickel plated object. Over here, this person is looks like they're electroplating some copper pots. So they place the object that they want to plate into the electroplating bath right here, and they have a copper source. You can see some copper metal. Okay, so the copper metal is getting transferred, okay, through the solution onto the cathode and plating it. And so you get a nice shiny coat of copper on these copper pots. And you can sell them as copper pots without making them out of pure copper. Here's some gold jewelry that's electroplated. Here's some silver plated stuff. Okay, gold plated watch. Okay, very nice way to make our objects more attractive by only using a very small amount of metal to do that. All right, and so in our demonstration today, this was an example of an electrolytic cell, the water destroyer. So if we want to split water and we want to change it, okay, into hydrogen and oxygen gases, then we're going to have to apply some electricity, because in nature, right, water does not naturally just split and turn into those gases. So we have to drive a reaction in order to produce those gases and force water to split and destroy it into those gases. So in this demonstration, we put in water with some universal indicator that changes different colors based on the pH. And you can see here on one electrode, we see the pH changing to a much lower pH than the pH 7 of the water. And on the other electrode, we see the purple appearing, showing that a much higher pH, a basic pH, is being created. So based on these colors, we would expect, right, on the red, where the red color is appearing, we must be producing some hydrogen ions, okay? And over here, where the color is turning purple, we must be producing some OH minus ions, okay? And if we look carefully, one of these has more gas coming out of it than the other. This one has more gas evolved, okay? And this has less gas on this side. All right, so we know that the gases have to be hydrogen and oxygen. So how do we know which side is producing the hydrogen and which side is producing the oxygen? And right, what does it mean that these are getting basic and this side is getting acidic? Well, we got to look at the half reactions from our standard reduction table, and here are the two that agree with what is happening at each electrode, right? So over here we have some H plus, okay? And so this is getting produced. So this reaction is not the one that's happening, right? You've got to flip this to show what's actually happening. So over here, right, in this reaction, we have our 2H2O, our water, getting destroyed into oxygen plus 4 H pluses plus 4 electrons. Okay, that's what's happening here, right? We're seeing some gas bubbles, some oxygen gas bubbles, and some hydrogen ion produced, changing the pH. Over here, this is where our water is getting destroyed. Okay, oh, we need some electrons here. And it is turning into hydrogen gas plus hydroxide ions. Okay, so on one side, water is getting reduced. Okay, over here, water is getting oxidized. Okay, and if you look at the actual oxidation numbers, you'll see here the H, right? The hydrogen is going from +1 to 0 it's going down, right? So it's getting reduced here. And then this oxygen over here on the right is going from -2 to 0. It's going from a negative number to a more positive number. So it is getting oxidized. So we have hydrogen getting reduced on one side and oxygen getting oxidized on the other. All right, so the overall net ionic equation, if you multiply this one by 2, okay, you're going to end up with 2H2O forms 2H2 plus O2. And so that's why we see more gas on this side, because we're producing twice as much hydrogen, okay, as oxygen over here because of that stoichiometry. So what's the minimum amount of voltage needed to get rid of to split this water, to destroy water, right? Since we're flipping this is the oxidation, right? We're going to take the reduction minus the oxidation, and we will end up with negative 2.06, okay, volts. Okay, so we need at least 2.06 volts to destroy some water here. All right, so the last thing we talked about very briefly was the Nernst equation. This is a very useful equation. It can tell us the cell potential at non-standard conditions. So here, our E with the little, okay, E naught right here, is the cell potential. This is the standard cell potential, and that's what we've been calculating using our half reactions and our standard reduction potentials. This is the non-standard cell potential. And this is useful because, right, not all cells are going to run at standard conditions, right? The standard conditions are 1 atm, 1 molar solutions at 25 degrees C, right? We're not always going to be there, so we'd like to know, okay, what's this cell going to produce if we're running it at this pressure and at these molarities and at this temperature. So this can allow us to calculate that. Again, here, this is our non-standard cell potential. Okay, N is our moles of electrons. Q is our buddy, the reaction quotient. So what we want to do is memorize a form. Well, we don't need to memorize it anymore because it's back on the equation sheet, but that the non-standard cell potential is equal to the cell potential, minus some blob right here, okay? Natural log Q. Now, I shouldn't call it a blob, but it's just some constant, okay? All of this, these are all numbers that are constants, and so you just have some large, some constant in front of the natural log of Q. So here, if we take a look at the reaction quotient, remember this part right here is just a constant. Okay, so just treat that as a constant. And the part that's going to concern us is the natural log of Q. So if Q is less than 1, okay, if Q is a number that's like 1 times 10 to the negative, negative 10, or anything with a negative exponent, right, you're going to end up with a natural log of Q that is less than 0. You're going to end up with a negative number, okay? So if Q is less than 1, if it's a decimal number, then if we take this as a negative, okay, negative quantity, and we have a negative of a negative, that turns this positive, and we add it to the standard cell potential to get a actual potential that is greater than the standard potential. Okay. Now the opposite's going to be true if Q is greater than 1. Q is greater than 1. We've got a number with a positive exponent. Okay. And so the natural log of Q then will be greater than 0. So this part will be positive. So if we subtract off the standard cell potential, we're going to get our actual potential to be less than, okay, the standard cell potential. And if Q equals 1, well, the natural log of 1 is equal to 0. Then this whole thing disappears, and we just have our actual potential to be the same as, okay, equal to our standard cell potential. So I hope that helps you think about different situations where with Q, okay, with the value of Q, and to know how the cell potential will relate when we have certain conditions, okay, when we have some concentrations here. And this example we'll go over on Thursday, but this the AP exam is never going to ask you to calculate the EMF is another word for E-cell. But you should be able to predict, okay, whether this cell voltage is going to be greater than, less than, or equal to the standard cell potential. All right, so the Nernst equation is the last topic in AP chemistry that I wanted to go over, and hopefully this video helped you understand and reinforce the concepts that you learned in class. And if you have any questions, let me know.